Okay, this is your third, I think, and last rotational kinematics worksheet. We'll do however many we can do in 15 minutes. You've got a tricycle wheel with a radius of 0.11 meter. It starts from rest. Then it's accelerated at 2.3 radians per second squared over a period of 8.6 seconds. And you want to know what's the final angular velocity. So let's just do what we always do. We underline. We write down what we have. It starts from rest. And then what's its final angular velocity? We have an acceleration of 2.3 radians per second squared and a time of 8.6 seconds. And so we're just going to use, this is a straight rotational problem. There's no conversions needed. And if you look at, you have essentially an analog of initial and final velocity, an acceleration and a time. So what we're going to do is, well, you remember Vf equals Vi plus At. So we just use the analog of that, which is Wf equals Wi plus alpha t. Wf equals 0 plus 2.3 radians per second squared multiplied by the time they gave us. It's just 8.3 seconds. And okay, the answer that I get is 19.19. I get 19 radians per second. The key says 20, but I'm going with this 19 because 2.3 times 8.6, let me double check. 2.3 times 8.6 is, well, the key is right. 19.78. I must have just made a mistake, which turns out to be 20, just like the key says, 20 radians per second. All right, messed that one up, huh? We've got a tricycle wheel with a radius of point. Actually, I think this is the same question. Yeah, it is the same question. So you've got this, you've got a final rotational angular velocity of 20 radians per second. What's the linear? And the way it works is the angular is the linear divided by r. So the angular is this. We want to find the linear, which is v. The radius is 0.11 meters. So yeah, the key says, when you do the cross multiplication, the key says 2.2 meters per second, and that is exactly what I get. Okay, you've got a potter's wheel, angular velocity, initial angular velocity of 3.2. We're told it has an acceleration of 0.21. What's the final angular velocity? This is just this is a straight well, like before, it's we're going to use the analog to this, that the final angular velocity equals the initial plus alpha t. The final we don't know. The initial is 3.2 radians per second. The acceleration is 0.21 radians per second squared multiplied by the t that they gave us is 6.4 seconds. Everything's in two significant digits, so let's see what we get. 0.21 times 6.4 equals plus 3.2, and you get 4.5 radians per second. So that's, no conversions needed. Pretty basic. The same potter's wheel. What are they looking for? Something different. It still has an initial angular velocity of 3.2, still has an acceleration of 0.21 radius. So everything's the same, but now they're just looking for the angular displacement, which is theta. What is its rotation? So when I look at this, I think of the equation, this equation becomes this. Alpha t squared. This is what we're looking for, so 3.2 radians per second multiplied by the time of 6.4 seconds plus 1/2 alpha 0.21 radians per second squared. Alpha t squared 6.4 squared. That's second. Running out of room over here. 6.4 seconds squared times 0.21 times 0.5 equals plus parentheses 3.2 times 6.4 end of parentheses, and you do get 25 radians. 25 radians. Alrighty. Bicycle wheel with a radius of 0.38, an acceleration of 4.8 radians per second squared. 9.2 seconds is elapsed. It starts from rest, an angular, with no angular velocity. What is this? Theta. So what's the angle? I think the analog is still d equals VIT plus 1/2 AT squared, which is theta equals omega t. So basically the same question with different numbers. This is basically, it is, no, it's not the same question. Okay, so you're starting with 0 angular rotation. The alpha is 4.8. The t is 9.2, but that gets squared. So I like to work backwards. I do 9.2 squared times 4.8 times 0.5 equals 203. Well, actually, hold on. Yeah, they're not looking for the radians. They're looking for the revolutions. But to get the revolutions, you have to get the radians. So I've got, let's see if I did it right, 203 radians. And then I do my conversions. How many revolutions? Well, one revolution is 2 pi radians. So these cancel out. So I have to multiply 203 times 1 divided by parentheses 2 times 3.14, and the parentheses equals, and it is in fact 32 revolutions. See what I did there? I had all this angular stuff, and I thought if I'm going to get revolutions, I have to find the number of radians, and then I'll just convert. I'll multiply by a conversion factor that each one revolution is 2 pi radians. Bicycle wheel, radius 0.38. It's got an acceleration of 4.8 meters radians per second squared over a time of 9.2. It starts with no rotation at all. It's no angular velocity, and they want to find out what's linear displacement. So if I'm going to find the linear displacement, I'll solve it as an angular problem and convert. The analog we're looking at is the analog to this, the rotational analog. Yes, I think I'm right. Theta equals WIT plus 1/2 alpha t squared. So WI is 0 plus 1/2 4.8 radians. Give me a second here. What am I doing? It's the same problem. So I'm making my life so much harder because I already have the radians, which is 203 radians. So that it was extra time. It's the exact same problem. So 203 radians from before. And theta, radians equals the d over the r. 203 radians equals the d that we want to find divided by the r, which is 0.38 meters. 0.38 times 203, 77 meters. So I made our life a little tougher, didn't I, there? I think, feeling like we need to do just one more. Frisbee with a radius of 0.15, or maybe two more because this is a follow-up. So you've got these two rotations and revolutions per second. You have to find the angular acceleration. So that's not good. We need radians per second. But I know that one revolution is 2 pi radians. And I could do that twice. Maybe I could 2 pi. Probably I should find, you know what? That's silly. Why don't I find the difference first and then do one conversion, right? Let's find the difference. Is that what we're doing here? We want to find, yeah, angular. So if I find let's find the change of, let's see, 9.3 minus 7.1 is 2.2 revolutions per second. Isn't that smarter? And then I just do one conversion. One revolution, I put it on the bottom so it cancels out, is 2 pi radians. And so 2.2 times 2 times 3.14 equals, so you have a change of W, yeah, of 13.816 radians per second. And I do know that alpha is delta W over delta T, so alpha is 13.816 radians per second divided by the time, 6.0 seconds. So let me just divide this by 6, and I get, yep, good, 2.3 radians per second squared. The rotational acceleration. Now I think I'm just gonna, then they want the, I thought this was gonna be easy. What's the angular displacement? Well, I might as well do it. Let me just do this, because it's, so we know that the change in, I'm going to leave this to the next one.